Hi everyone, we're moving on to Unit 3. Okay, so Unit 3 is going to look at something that largely seems very different than what we've done so far, which is focus on derivatives and integrals, but we will use all of those concepts throughout this unit. This unit is going to look at infinite sequences and series. Okay, so an infinite sequence is just a succession of numbers, but it continues indefinitely. Okay, so it goes all the way to infinity. And an infinite series is just simply the sum of that sequence. Okay, so if you had a sequence of numbers 1, 2, 4, 8, okay, this you would call an infinite sequence. Okay, an infinite series would be if you added the sum symbol behind it. So if you added up all of those terms, so if you had the sum of all these terms, 1, 2, 4, 8, we kept going, this is an infinite series. Okay? So we're going to look at these in many different ways. Okay, different types of series that have different uses. All right, so each type of series we look at has different basic properties, and because of that, they have different uses. Okay, so what we're going to start off with is just to talk about series. Okay, so for an infinite series, you're obviously not going to add up a lot of it or add up every single term in most cases. Okay, so you might only add up the first couple terms, maybe 3 terms, 4 terms, 6 terms. Okay, or when we get into later series, you might only calculate the first 3 or 4 terms, and that's common. And what those are known as are partial sums. Okay, so we denote a sum by the letter S. Okay, and in this case, S1 is the sum of just the first term. S2 would be the sum of the first 2 terms. S3, the sum of the first 3 terms, etc. These are known as partial sums because they're not the whole sum of these series. But what you'll see is as you get further and further along, we're going to see that they'll likely converge to a number. So in a lot of instances, you don't have to add up all the terms to infinity because you can figure out rather quickly whether it's going to converge to a certain number after you do a certain number of these sums. Okay? So what you'll notice is these partial sums, they also form a sequence, right? So we showed that the S1 was the sum of the first term, S2 was the sum of the first and second term, S3 was the sum of the first, second, and third term. And it continues on all the way to our last one, which would be S to the n, where that is equal to the sum of the n number of terms, whether n is 100, okay, 1,000, or if n starts to approach infinity, which is where the majority of these series will go to. So if you want to find the sum of these series, we can't just put it as infinity. We can't have just n being infinity. Remember, a lot of times where we saw infinity, we used limits. So limits are going to be important here as well. Okay. So what we do with a limit is, remember, you often tried to see if a limit existed. Because if you just substituted in infinity, you couldn't solve for that value. It might come out as infinity, or it might come out as something divided by 0, or 0 divided by 0 when we did L'Hopital's rule. So what you do, but what it does do is if you went just before, okay, infinity, you might get a number like 2, okay? Because if it goes any further to that number, that number doesn't exist. It can't reach that. So we use limits here as well. And what we do is we find the limit as n approaches infinity, if we want to add up these whole series, of that sum. Okay, so as we add up an infinite number of terms, what does that limit come to? And what we're looking for is whether the limit exists or not. Remember, sometimes you had a limit of a function and it just didn't exist. In this case, if the limit doesn't exist, it's known as divergent. And we'll look at an example of what a divergent series is. If the limit does exist, what it means is that the sum of this series comes to a certain number. 2, 2/3, 10, okay? Something like that where it converges to a specific number. So we're going to look at examples of both so you can see what I mean when I say convergent or divergent. Let's start with a divergent infinite series. So for an infinite series to be divergent, the limit doesn't exist, like I mentioned. And what that means is that the series continues to grow. Okay, so it exponentially grows and there isn't actually a specific number it converges to. A good example of that, okay, is any number to an exponent. So if we had a series, okay, the sum of n equals 1 to infinity of 5 to the exponent n, okay, what this means is it's the sum starting in n equals 1 and adding a term each time. So 1, 2, 3, 4, 5, all the way to infinity. Okay, so that's what this sum term means. So what it means is we have 5 to the exponent 1 plus 5 to the exponent 2 plus 5 to the exponent 3 all the way to 5 to the exponent n. However far we take this, if we go all the way to the end of the series, we'd have 5 to the exponent infinity. Now what you'll notice is it's really beneficial to try doing this using partial sums first. So we can look at, let's say in this instance, the first 3 partial sums. So we'll look at the first sum, which is just the first term, 5 to the exponent 1, or 5. If we look at the second term, it's 5 to the exponent 1 plus 5 to the exponent 2, which comes out to 5 plus 25, or 30. The third partial sum is 5 to the exponent 1 plus 5 to the exponent 2 plus 5 to the exponent 3. Again, as you can see, what this sum term is telling you is that the value of n increases by 1 each time, okay, all the way to infinity. So for our third partial sum, we have 5 plus 25 plus 5 to the exponent 3, which is 125, or 155. So what we see here is the sequences keep growing. They don't actually, the sums don't actually converge toward a specific value. So from looking at this, we can say it appears to be divergent. Okay, I will show you a rule to figure out whether it's convergent or divergent. But from just looking at partial sums, it does appear to be divergent. Let's look now at a convergent infinite series. So for a series, an infinite series to be convergent, the limit that we talked about has to exist. Okay, so the limit we had as n approaches infinity of that partial sum, remember it's n. Okay, so as it approaches infinity, meaning it has all the terms, this has to come out to something, okay? A number, it has to exist. If it comes out to infinity, then we know it doesn't exist. So let's look at the same example, okay? What you're going to see is when I say it converges to a number, you're going to see it very quickly stops growing or is growing at a slower and slower amount each time, okay? So the same example, 1 divided by 5 to the exponent n. Okay, remember the last example was just 5 to the exponent n. The other change here, okay, is we're starting from n equals 0 to infinity instead of n equals 1. You will see some infinite series as n equals 1 to infinity, and you will see some as n equals 0 to infinity. It's a small difference, and it doesn't necessarily affect everything else in the series, as you'll kind of see. The only thing it affects is your first sum would therefore be S0, okay? So if we have 1 divided by 5 to the exponent n, we start with 1 divided by 5 to the exponent 0, plus 1 divided by 5 to the exponent 1, 5 to the exponent 2, 5 to the exponent 3, all the way to 1 divided by 1 divided by 5 to the exponent n. So looking at our partial sums, our first sum is S0, which is 1 divided by 5 to the exponent 0. Remember, anything to the exponent 0 is 1. So that becomes 1 divided by 1, or just 1. S1 is equal to 1 divided by 5 to the exponent 0 plus that second term, 1 divided by 5 to the exponent 1. So we're left with 1 plus 1 over 5, which is 1.2. Our third sum, okay, we're calling it S2 because remember, we have S0 because we have for n equals 0 here. Our third sum, S2, is 1 divided by 5 to the exponent 0 plus 1 divided by 5 to the exponent 1 plus 1 divided by 5 to the exponent 2. So we have 1 plus 1 over 5 plus 1 over 25, which gives us 1.24. So you can see this grew by 0.2, this grew by 0.2, this grew by 0.04. The fourth sum, okay, we're calling it S3, again, remember, because of the S0, is 1 divided by 5 to the exponent 0 plus 1 divided by 5 to the exponent 1 plus 1 divided by 5 to the exponent 2. So that's everything from the previous sum plus 1 divided by 5 to the exponent 3. So we have 1 plus 1 over 5 plus 1 over 25 plus 1 over 125, which gives us 1.248. So you can see here, this change is now 0.008. So every time the incremental increase is going down, okay? So as you get further and further and further, these numbers are going to get smaller and smaller and smaller. And what you can see is it's converging towards a certain number. And what it looks like approximately is 1.25, okay? So in this case, we can say that it appears to be convergent to approximately 1.25, all right? So these partial sums, or looking at the first, 3, 4, 5 terms is very helpful in all of these cases, okay? They can provide the majority of the information that you need. So don't be kind of intimidated by the fact that these go to infinity, okay? Because oftentimes we're going to look at the first group of terms only. Okay, so let's look at another example. So I've showed you an example of a divergent and a convergent series. We're going to look at one more, okay? Determine the first 5 partial sums of the following series and determine whether the series appears to be convergent or divergent. So our series is the sum as n equals 0 to infinity of 1 over 2 to the exponent n. So that is equal to 1 divided by 2. And the first term in this, remember, is n equals 0. So it's 2 to the 0. Plus 1 over 2 to the exponent 1. Plus 1 over 2 to the exponent 2. Okay, all the way to 1 over 2 to the exponent n. Okay, I like to write that out to give myself a baseline just to know kind of what this series would break out as. Now, to determine the first 5 partial sums, okay, we're starting at n equals 0. So we're going to have our sum of S0, S1, S2, S3, and S4. Okay, so you can see it's 4 here at the end, but if you count these up, it's 5 partial sums. The first partial sum, S0, is the first term, okay, which is 1 divided by 2 to the exponent 0. Remember, anything to the exponent 0 is 1. So this becomes 1 divided by 1, or simply 1. The next partial sum is the first 2 terms. So 1 divided by 2 to the exponent 0 plus 1 divided by 2 to the exponent 1, which is equal to 1, okay, for the first term, plus 1 over 2, or in other words, 1/2. So you can write it as 1.5 or 3 over 2. The third sum is the first 3 terms. 1 over 2 to the exponent 0 plus 1 over 2 to the exponent 1 plus 1 over 2 to the exponent 2. So in this case, we get, remember, 1 plus 1/2. Okay, so it's always going to be the terms from the previous partial sum. Plus, in this case, 2 squared is 4, so we have 1 over 4. So this gives us 1.75, okay? Or you could technically write this as something like 7 over 4, okay? Either or, when you start getting into later sums, you're going to realize that fractions become more difficult as the sums get larger, okay? So oftentimes, a lot of you will prefer to write them in decimal form, and that's entirely fine. Our fourth sum is the addition of the first 4 terms. So 1 over 2 to the exponent 0 plus 1 over 2 to the exponent 1 plus 1 over 2 to the exponent 2 plus our fourth term, 1 over 2 to the exponent 3. So in this case, you can either write them all out like I've been doing here, okay? Or you can start with the partial sum from the previous one. So you know that this is 1.75 plus your final term, right? Because you're adding one term each time. And in this case, the last term is 1 divided by 2 to the exponent 3, which is 1 divided by 8. And if you do that, in this case, you'll get 1.875. Okay? Our last one, S4, is the first 5 terms. So 1 divided by 2 to the exponent 0, plus 1 divided by 2 to the exponent 1, 2 to the exponent 2, 2 to the exponent 3, and our last term, 2 to the exponent 4. So in this case, remember, our previous sum was 1.875, and we added this 1 divided by 2 to the exponent 4. 2 to the exponent 4 is 16, so this is plus 1 over 16. In this case, that equals 1.9375. So you can see that it's still growing, all right, but it's getting smaller. So from here to here, I'll do a different color. From the first sum to the second sum, it increased by 0.5, and it increased by 0.25 to the next sum, and then 0.125 for the next sum, and then for the last one, 0.0625. Okay, so you can see it's decreasing, but it hasn't quite gotten to a point where it's stabilized. Remember when we had 1 divided by 5 to the exponent n, it stabilized rather quickly to 1.25. In this case, it appears convergent, okay? So I can write yes, it appears convergent, and I write it with a question mark, okay? Because we don't know for sure what we think it's coming to as a solution. If I had to make an estimate, I would say 2, but we don't know that yet, okay? Which is why you'll also see in my solution, I write yes with a question mark, because we can't prove definitively using this that it is convergent. So as you saw in that last example, if we kept continuing to find partial sums, we probably would have arrived at a certain number that it converged to. But what we want to look at is there a method to, number one, or part, I guess A, calculate or determine convergence of a series, and B, determine actually what it converges to? The answer to that is, unfortunately, it depends. Okay, we're going to see a lot of different types of infinite series. The ones you've seen so far, there is a method to determine convergence. Okay, these series are known as geometric series. Okay, what they have in common is a common ratio between them. So if you were to write these series out, okay, you could write the partial sum, S to the n, as the first term that you calculate out plus the second term multiplied by this ratio r, plus the third term, which is this, again, the starting term multiplied by the ratio r squared, continuing on, because the difference between one term and another is this common ratio. When I say ratio, I mean it's a multiplier in between them. Okay, so an example of this is, look at the last example, 1 over 2 to the exponent n. Okay, so we had the sum of n equals 0 to infinity. So if we started this out, we got 1 over 2 to the 0 plus 1 over 2 to the 1 plus 1 over 2 squared, and it kept going. You could write these out as 1 plus 1/2 plus 1/4 and keep going. What you notice, okay, if you look between these, is each number is 1/2 of the previous number, right? So 1/2 is half of 1. 1/4 is 1/2 of 1/2, okay? So there's a common value in between. So you technically could take the previous number and multiply it by that ratio, okay? So the ratio for this would be 1/2. Okay, and that's what a geometric series does. Okay, you can use that ratio to find any term technically within this infinite series. So this ratio is something we're going to talk about next, and how to calculate it, and it becomes the central piece to how we determine convergence, all right? So, like I said, you could use the previous term to calculate the next term if you know what the ratio is. So the ratio is actually the current term you're looking at divided by the previous term. Okay, so going back to our example, the sum of n equals 0 to infinity of 1 over 2 to the exponent n. We had 1 divided by 2 to the 0, 1 divided by 2 to the 1 were the first two terms. So what those were are 1/2 and 1. So if we looked at calculating our ratio, we could substitute those in, okay? So our second term is 1/2 divided by the term that came before it, which is 1. So in that case, our ratio is calculated out as 1/2. Now, for it to be a geometric series, you could do that for any of the terms, okay? So if I continued this out and I did 1 divided by 2 squared, 1 divided by 2 cubed, and it kept going on. If I look at the next two terms, we'd have 1 over 2 squared, which is 1/4, divided by the term before it, which was 1/2, okay? So taking these terms and placing them there. If you calculate that out, 1/4 divided by 1/2, again, is 1/2, okay? So in a geometric series, this ratio is always the same between terms directly beside each other in the series, all right? And that ratio becomes important because it allows you to determine convergence. So to find whether or not this series converges to and whether or not it actually converges, the formula is actually the first term, so a1, divided by 1 minus this ratio. So keep in mind, for this case, it's either going to be a1 or if n is 0, it actually becomes a 0. Okay, so it's the very first term that you calculate. All right? An important thing to note about this determines, okay, the actual sum. Okay, so this will determine the sum that it converges to. The ratio will determine whether or not it converges. So if the value of the ratio, the absolute value, is less than 1, the series converges. If the absolute value of r is not less than 1, okay, so let's say it's 2, 3, 4, 5, it will diverge. Okay, so what you'll notice here is you won't actually be able to calculate the sum using this. Okay, it's only valid for when the series converges. All right. So to prove this, I want to look at all three of our examples once again. Okay. So we'll start with our first example, 5 to the exponent n. Our first term, okay, if we multiply this out, we get 5 to the 1 plus 5 to the 2 plus 5 to the 3, okay? So what we're looking for in this are the terms, okay? We're not looking for the partial sum. So the first term, remember we called them a1, a2, a3 when they were just the terms, was 5 to the exponent 1, which gives you 5. Okay, remember that's the first term here. The second term was 5 squared, which gives you 25. Okay, again, the second term here. So our ratio, okay, would be our second term divided by our first term, okay? So you always look at the kind of latest term and divide it by the one directly behind it. In this case, we have 25 divided by 5, or 5. So our ratio is not less than 1. So what this means, since our value for r, okay, is greater than 1, okay, it will diverge. And we saw that it diverged, right? Because it just kept expanding. Looking at our next example, we had 1 divided by 5 to the exponent n. Again, in this case, it was starting at n equals 0. So what we had here was 1 divided by 5 to the exponent 0 plus 1 divided by 5 to the exponent 1, 1 divided by 5 to the exponent 2, and it kept going. So our first term, okay, is 1 divided by 5 to the exponent 0, which is 1. Our second term is 1 divided by 5 to the exponent 1, which is 1 over 5. So our ratio is our second term divided by our first term, or 1 over 5 divided by 1, which gives you 1 over 5. Okay, so since this value, okay, is less than 1, it should converge. So we can actually calculate what it converges to. Remember that sum is equal to the first term, in this case a 0, because it's our first term, divided by 1 minus this ratio. If we do that, our first term is 1, and it's divided by 1 minus 1 over 5, which gives us 1 divided by 4 over 5, or in this case, 5 divided by 4, which is 1.25. Remember, that's what we thought it converged to approximately, was 1.25. So this shows you what it will converge to. Again, this is for geometric series that follow this common ratio. Our last example, 1 divided by 2 to the exponent n. Remember, we did all those terms, and we thought maybe it comes to a value of 2, but we didn't know that for sure, okay? Because we needed to calculate more terms. So if we have this, again, we're starting at n equals 0. If we expand this out, we have 1 divided by 2 to the 0, plus 1 divided by 2 to the 1, 1 divided by 2 squared, and it keeps going. So our first term, 1 divided by 2 to the exponent 0, is 1. Our second term, 1 divided by 2 to the exponent 1, is 1/2. So our ratio is our second term divided by our first term, which is 1/2 divided by 1, which gives us a value of 1/2. So again, since our absolute value for r is less than 1, it should converge. And what it'll converge to, our sum, is equal to our first term, again, a 0, divided by 1 minus our ratio. So a 0 is 1, and we have divided by 1 minus our ratio, which is 1/2. And if you calculate this out, it comes to 2. So you can see my estimate of 2 turns out to be what this sum will actually converge to. All right? So using this formula, you can see that if you don't get the ratio, okay, that's less than 1, so if you look back to this first example, you know it diverges. You can't calculate that sum because it just keeps growing to infinity. But in the other cases, you're actually able to find rather quickly, using a small number of terms, the value it converges to. Okay, so let's look at 2 more examples. First example, determine if the series below converges. If it converges, calculate the sum. Okay, so I'm not asking you to do any partial sums here, but remember what we're going to do first is calculate the ratio to see if it converges, and then we're going to calculate the actual sum if it does in fact converge. So remember, your ratio is a to the n divided by a to the n minus 1, or the next term in the sequence divided by the previous term. So for this, it's the sum as n equals 0 to infinity of 1 over 3 all to the exponent n. So if we were to expand this out, we'd get 1 over 3 to the exponent 0 plus 1 over 3 to the exponent 1 plus 1 over 3 to the exponent 2, and keep going. So our first term, a0, is equal to just 1, because 1 over 3 all to the exponent 0 is 1. Our second term here is 1 over 3 to the exponent 1, which is just 1 over 3. So what we have here for our ratio is we'll start with the second term, a to the exponent 1, and that's divided by a to the exponent 1 minus 1, or a to the 0, so the first term. Substituting our values in, we get 1 over 3 divided by 1. So our ratio here is 1 over 3. And remember, the absolute value of the ratio has to be less than 1 for it to converge. In this case, 1 over 3 is less than 1, so we do know that it converges. Okay, so since it converges, we can calculate the sum. So the sum, in this case, remember, is our first term, which is a 0, in this case, divided by 1 minus our ratio. So our first term, a to 0, is 1, and it's divided by 1 minus our ratio, which is 1 over 3. So we end up with 1 divided by 2/3, which comes out to 3 over 2, or 1.5. Okay? So you can see the difference in this test is we aren't calculating a bunch of partial sums this time, right? We're figuring out whether it converges much faster. Okay, so let's look at our second example. Determine if the series below converges. If it converges, calculate the sum. In this case, we have the sum from n equals 1 to infinity, not 0, of 1 divided by -4 all to the exponent n. So this simplifies out to 1 over -4 to the 1 plus 1 over -4 squared plus 1 over -4 cubed, continuing out. Okay, so what these would simplify to, our first instance is -1 over 4. Our second one, -4 squared is positive 16, so we'd have plus 1 over 16. -4 cubed is negative 64, so we'd have minus 1 over 64, and plus the rest of our terms. So to calculate, we start with our ratio. Our ratio in this case would be a to the n divided by a to the n minus 1. And again, because it's a geometric series, we don't have to pick the first two terms, but oftentimes we do, because then you don't have to calculate as many terms. Okay, so if we do that, we take our second term, 1 over 16, divided by the term directly before it, -1 divided by 4. And if you calculate this out, you can use your calculator or you can use dividing fractions. You'll get -1 over 4 or -0.25, depending on if you put it in your calculator. Now remember, to check if this converges, our ratio, absolute value of it, has to be less than 1. So the absolute value of this is less than 1 because it's 0.25. Okay, so we know that it converges. Right? To calculate our sum is equal to our first term, which is a1 in this case, not a0. Remember, because our sum started at n equals 1, divided by 1 minus our ratio. So in this case, our first term is -1 over 4, and it's divided by 1 minus our ratio, which is -1 over 4. Okay? So this becomes -1 over 4 divided by 1 minus 1/4 is 1 plus 1/4, which gives us 5 over 4. And if we calculate this out, we get -1 over 5, or -0.20, depending on if you did fractions or if you put it in your calculator. So we see that the sum of this is actually a negative number. Okay, so it actually converges to -0.20. And when you start looking at these sums, you can start to realize that the first term, especially in this type of series, the first term is always going to be the largest, because as the denominator increases, these numbers get increasingly smaller. So your first term here was negative, right? -1 over 4 is -0.25. So as you're adding and subtracting additional terms, right, because this negative sign causes it to flip between negative and positive, your largest term here is still a negative number. So it's not surprising that your overall sum remained a negative number. Okay? So you're probably wondering, what if the ratio is not consistent between terms? So in each of these instances, we had geometric series where the ratio in between all the terms was consistent. Well, what if we had something like the sum from n equals 0 to infinity of 1 over n plus 2? Well, the first term is 1 over 0 plus 2, which is 1/2. The second term would be 1 over 1 plus 2, which is 1/3. The third term would be 1 over 2 plus 2, which is 1/4. Okay? So if we calculate the ratios between these, if we do the ratio between the second and the first term, we have a1 divided by a0, which is 1 over 3 divided by 1 over 2. If you calculate that out, you get 2/3. The ratio between the third term and the second term, again, it should be the same. It doesn't matter which terms they are in the series. The ratio in this case would be A2 divided by the term right before it, A1, which is 1/4 divided by 1/3. Calculating this out, you get 3/4. So you see that they're not consistent. And what that means is that it's not a geometric series. It's a different type of series. Okay? These types of series fall into usually what's known as harmonic series, which we'll talk about later on. But it simply means that it's not a geometric series. So it will be one that we talk about later on in these lessons. Okay? So this lesson focused specifically on geometric series. So that was all I had for this lesson. I do recommend, before we get into specific types of series, the next lesson we'll talk about Maclaurin series, you do some practice problems with this and start getting used to seeing that sum symbol. Okay, so the sum, in this case, of n equals 0 to infinity, or maybe the sum of n equals 1 to infinity. Get used to seeing those symbols and understanding kind of what they mean, and then get used to writing out the series. So if you had, again, 1 over 2 to the exponent n, get used to writing them out. 1 over 2 to the 0 plus 1 over 2 to the 1, okay? Because writing them out, you'll see, will be fundamental to doing other types of series that are even different than this. Okay? If you have any questions, please feel free to send me an email. I'll try and respond as quickly as I can. Thanks, everybody.